Welcome to Maths with EJD. In this video, we're still talking about sequences and series, and now we get to talk about series proper because all along I've been talking about sequences. I haven't talked about types of introduction to sequences, arithmetic sequences, geometric sequences, and in the last video, recursive sequences. So here, let's talk about series and start with the definition because what you define is what you find, like someone said. Definition of a series. Definition of a series. A series is the sum. A series is the sum of the terms of a sequence. Okay? When you sum up the terms of a sequence, you get a series. And that is why series and sequences go together. All right? So if the sequence AN is a sequence, if this is a sequence, the corresponding series is S, which is A1 plus A2 plus A3 plus all that, all right? And that is equal to summation from N equals 1. Okay, I mean, this is up to N. From N equals 1 to infinity of AN, okay? That is the series of that sequence AN, okay? Now, having talked about this, let's move on and talk about the sum of the terms. The sum of the terms of a sequence, of course, which you have seen that can easily be called a series. So can we talk about the sum? The sums like that. So a finite series sums a specific number of terms, a specific number of terms from the sequence. Okay. So if you have a sequence and you sum up a specific number of terms of that sequence, so in that case, you say you have a finite series. So the series will be finite in that situation. Okay. On the other hand, for infinite series, okay, the sum includes all terms, extending to infinity, Okay. So, infinite series, you sum all terms of a sequence included, all the terms of a sequence up to the end, up to infinity. Like imagine if I have a series of natural numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on and so forth. So if I sum from 1 to 10, which will give me 10 times 11 divided by 2, that's like 550, right? That is a finite series. But if I sum up everything and say 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 down to the end, down to infinity, in that case I have an infinite series. Okay. Now, mathematically, mathematically, this is written, this is written as a limit. It is written as a limit of partial sums. I mean, this idea of partial sums is really important in series. So partial sums. So here we now have something like Sn is equal to summation from n equals 1 to n of an. Okay. So this is like the whole series, right? So that is when you talk about an infinite series. This is for an infinite series. So you can have this, and you can also have this other one where Sn is equal to the limit as n tends to infinity. Okay, as n tends to infinity for that Sn at the top there. For that Sn, if that limit exists, if the limit exists. So basically what we're saying is that this expression is the partial sum. Okay, this is the partial this is the finite series, sorry. This is finite series, you know. It's finite series because you start from n equals 1 and you end at big N. Finite. But here, so for that so-called finite series, right, you are taking the limit of the finite series as it tends towards infinity. So you end up with an infinite series. Okay? So that goes. Next thing to talk about is convergence versus divergence. Convergence versus divergence. Okay, let's talk about that. Convergence, convergence versus divergence. Now, this is really important when we talk about series again. You know, I have a whole playlist on power series, and we talked about convergence and divergence a lot. So normally, power series should also come under sequences and series. But what I'm going to do is when I get to that part of power series, I may just add the playlist from power series to this, so you can see it as a continuous flow like that. Okay. So here, can we talk about convergent series? Convergent series. So for a convergent series, right, approaches, the series approaches a finite value. The series approaches a finite value as n approaches infinity. So we are going to see very good examples, maybe in the most likely in the next video. Okay. The next 5 videos after this, we'll be talking about test for convergence. So watch out. It's going to be very interesting. So we'll test for convergence using different methods. So the series approaches the finite value as n approaches infinity. That's for convergent series. What if a series diverges? What happens? So we talk about divergent series. So for a divergent series, what are we talking about? In this case, the series does not the series does not approach a finite value. Okay, the series does not approach a finite value. That means that it may grow indefinitely, or it may oscillate. It may oscillate. Okay. So those are the differences between convergent and divergent series. Now, can we talk about something really important? Okay, drag that down. That's my aim. Okay. Let's talk about something equally important. Just like we talked about how to visualize sequences, right? By plotting the number of terms against the sequence value itself. We can do something close to that for partial sums. So visualizing partial sums. Okay. Visualizing partial sums. So let's see how that works. So if we talk about partial sums, right? Partial sums represented by Sn, okay, uh, represent, they actually represent the cumulative total, the cumulative total of the first first n terms of the series. Okay, that is what we mean by partial sums. Of course, I'm going to demonstrate that pretty soon. All right. So partial sums Sn represent the cumulative total of the first n terms of the series. Okay. So okay, I guess I can demonstrate that right now, so that imagine you have a series, you have S to be, say, A1 plus A2 plus A3 plus A4 plus A5 plus A6 plus all that up to plus AN. So we are saying that S1 is equal to A1. Okay. Talking about partial sums now. S2 is A1 plus A2. S3 is A1 plus A2 plus A3. All right. So it can keep growing like that until you get to the whole Sn where you have A1 plus A2 plus A3 down to the last, which is AN. Okay. These are partial sums now. So S1, S2, S3, and it goes on until you get to the last, which is Sn. Okay. Now, having talked about that, we can also plot. We can plot, right? We are talking about how to visualize this. So by plotting Sn against by plotting Sn against n, we can observe whether it stabilizes. We can observe whether it stabilizes. Stabilization means it converges or grows without bound, meaning that it diverges. Okay. So we have that. So can we take an example of this kind of visualization I just talked about? So let's imagine this example. So we have this example talking about arithmetic series. Infinite arithmetic series. Okay. So we have that. So infinite arithmetic series is what we are looking at in this particular example. So that we have this, consider the series where an is equal to 3n. Okay, an is equal to 3n. What that simply means is that we have s to be, our s here is just simply going to be 3. I think it's more intuitive to go this way. So it means if we're going to have a series of that, right? If an is 3n, so it means that we have summation from n equals 1 to infinity of 3n. That simply means we have 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 plus 3 times 12. I mean 3 times 4. And that goes on forever. Okay. So that the partial sum now is just 3 plus 6 plus 9 plus 12 and so on and so forth. Okay. We have this. So can we talk about the partial sums in this situation? Let's consider the partial sums. Partial sums. Okay. So for the partial sums, S1 is simply 3. Okay. S2 is 3 plus 6, which is 9. Then S3 is 3 plus 6 plus 9, that is 18, right? Then we have S4 also. You have S4, which is 3 plus 6 plus 9 plus 12. That's 18 plus 12, which is 30. Okay. So if it stretch that and we go all the way to Sn, that means we simply have 3 plus 6 plus 9 plus all that to whatever. And that means we have 3 into 1 plus 2 plus 3. Of course, all the way to 3n, right? As you remember. So all the way to 3n. So that means we have 3 into 1 plus 2 plus 3 plus everything up to n. Okay, up to n. If that is the case, it means that we have 3 out here. And in fact, this is one of my favorite things, that if you want to add from 1 to any number, okay, what you just simply do is you take the number, like you want to add from, let me just take a detour. I mean, let me just get to the small distraction. So if you want to add from 1 to 10, for instance, instead of just having to say 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, the smart thing to do is just go to the last number 10 multiplied by 11 divided by 2. So that would be 2 here is 1, 2 here is 5, and the answer is 55. And that's actually correct. So, and that's why you can easily add from 1 to 2000 without stress, and that would just be 2000 times 2001 divided by 2. So that'll be 1000 times 2001. So that's 2001, then three zeros, and that'll be 2,000,000 basically. So that makes it really fast to handle. Okay, so if you want to add from 1 to any number, just go to the last number, multiply it by the next number after it, and divide by 2, and you have your answer. So in that case now, since we have 3 outside the bracket, so this whole expression now is going to be so we now have 3 times. So this whole expression in green now is just going to be n into n plus 1 divided by 2, because we are adding from 1 to n, and that is exactly what we have right there. So here we see that Sn is equal to, if you like, you can say 3 over 2 into n, 3 over 2 n into n plus 1. You can actually do it this way. So this is the sum of partial sum up to n. So from this expression, right, does this series converge? That's the question we are asking. So, or does it converge or diverge? So to check, to check, to check for convergence, so to speak, to check for convergence. So what we now need to do is this. We just say so it means we're just looking for limits as Sn as n goes to infinity. That means we have limits as n goes to infinity for 3 over 2 n into n plus 1. Okay, so that this will just be 3 over 2 is constant, so we have limits. I've done all this under calculus. If you check the playlist on basic calculus, we did a lot of things on limits and continuity. So this is limit as n goes into n plus 1. So there's no how you're going to do this really, because if you substitute directly, you're just going to have infinity all the way. So it's more like you have 3 over 2. If you substitute infinity for n, which is the first thing to do, infinity plus 1, we cannot simplify this expression. So we just have 3 over 2 times infinity. So everything is infinity at the end of the day. So we can say, therefore, limit of Sn as n goes to infinity is equal to infinity. And the implication of that simply is that we can say, thus, the series diverges because the partial sums grow without bound. Partial sums grow without bound. Okay, so we can visualize this just like we suggested the other time. We can visualize this, and so that will be okay. Yeah, to visualize this now, let me try to let me change the view of this. I think it's possible. Let me change the view. I want to make it into something like graph format. Okay, I guess this is too big. Let me change it to a graph that can, okay, maybe this. Yeah, I think this should really help. So imagine that we want to visualize this, because we're talking about visualizing, talking about visualizing partial sums, right? And from what we have seen so far, so let's imagine that we have, just rule this. That's really wobbly, but we can manage. Okay. Okay, I guess I need to expand this now so it can be easier. Okay, so imagine we have this. Is this the best graph I can use, really? Okay, I think I need something bigger. I need something bigger. Let me go back and get that bigger one. I think that should help better. Um, I guess this should work. Yeah, this is finer. This is better. This is better. All right. So we have, imagine we have this kind of graph. So it's still wobbly, but thankfully we have, the graph is to scale, so we are good to go. So on this side, we are going to have number of terms. So here we're going to have number, we have number of terms, number of terms, which is n. And on this other side, we have partial sum. We have partial sum, which is Sn. Okay. And how do we label this? We can label it 1 to 10. So this is, we can say 2, 4, 6, 8, and 10. Okay, 2, 4, 6, 8, and 10. Or we can even do 12. All right. So 1, 2, 3, 4. So on this other side, we can have say this is, can I even do this? This is 20, this is 40, this is 60, this is 80, this is 100, this is 120. Or should I even make it bigger? Okay. So let me use two boxes for 20, right? Let me use two boxes for 20. Don't forget, these two partial sums. I'm going to rewrite that. So let me use two boxes for 20. Okay. Okay. I mean, this should still go. So now this is 20. This is 40. This is 60. This is 80. This is 100. This is what next is 100, right? Next is 120, right? Then next is 140, and then we can go one more and have 160, and this goes on like that, just like that goes. So this is partial sums. We have partial sums, which is Sn, partial sums, Sn. This is the origin. Okay. So this is the origin. So, I mean, for that partial sums we did, right? The partial sum we are considering is actually, we are considering partial sums of the series, summation from n equals 1 to infinity of 3n, or better still, 3n like this. And from what we saw, right, we saw the first three terms that we got were, so we got 3, 9, 18, 30, 3, 9, 18, 30. So it means the first one, number one is 3, somewhere around here. You know, this is 10. So number one is 3. The second one is 9. 9 is somewhere close to this. Then the third one is 18. The third one is 18, somewhere like this. Then the number 4 is 30. So number 4 is 30, right? 4 is 30, which is exactly here. Now, 5, 5 is 30 plus, after 12, right? 30 plus 15, that's 45, okay? 45. So number 5 is 45. So number 5, this is 40, this is 50, so 45 is somewhere around here. Then number 6 is 45 plus 18. 45 plus 18, that should be 63. Okay. So the next one is 63. This is 8, right? Number 7 is 63. 7 is 63 around here. What about number 8? That's 63 plus 21. 63 plus 21. That is 84. Okay. That's 84. So number 8 is 84. Number 8 is 84. So this is 90. 84 should be somewhere around here. Then number 9, what is number 9? That's 84 plus 23. 84 plus 23. That is 184 plus 23. That is 107. Okay. So the ninth one is the ninth one. Oh, am I getting that right? Okay, let me go again. Let me just be careful. The number 4 is 30. Okay, number 4 is 30. I hope you know what I'm doing, right? I'm looking at 3 plus 6 plus 9 plus plus 12 plus 15 plus 18 plus 21 plus 24 plus 27 like this. So this is 9. Okay, so the first, okay, sorry. We have the first one, which is 3. Then next we have 9. So number 2 is 9. That's why we have this 9 here. Number 3 is 9 plus 9. That's 18. So number 3 is 18, somewhere around there. Then number 4 is 30. So that's why you have 4 against 30. Number 5 is all right, 30 plus 15, that's 45. So this is 1, 2. Okay. Or instead of just doing that, this is S1, S2, S3, S4, S5. So so the fifth one is actually 45, which is fine, I think. Then the sixth one, S6. So that's 45 plus 18. That is where we got 63. That is S6. So 6 is against. Okay, I think that's where I made a jump, which shouldn't have been. So 6 is 63. So for 6 now, we have 60. This is 60. This is something like 63 around here. Okay. Then S7. So S7 is 63 plus 21. That's 84. That is S7. So 7 is against 84. So we have 7 against 84, somewhere around here. Then we go for the 8. 8 now is 84 plus 24. That's 108. I think this is easier to visualize. So the 8 partial sum is 108. That's for 8. So 8 against 108. So this is 8 against 10. This is 110. This should be 108. Then we have the ninth one will be 108 plus 27. That's 135. Okay. 135. That is S9. 135, I believe. Yeah, 135. So 9 against 135. So this is 9 against 1 3. This is 130. So 135 should be somewhere around here. Then the 10th one, if you go to, if you now have a 30, so that is 165. Okay. That is S10, this 10 partial sum. So that's 165. So that means that no, the 10th one is against 165. This is 165 is somewhere around here. So if you join that together, you can see that exponential curve. I hope I can join it well. So if some points are not hitting it, it's because I didn't do it well. So if I visualize it well, it would have been better. So this is it. Okay. So that is how to visualize partial sums. And you have also seen how to do the S1, S2 thing like I demonstrated before. So, I mean, that's how this has been talking about infinite series and whether they converge or not. Okay. So we have seen that this particular series, just like we proved here, it goes to infinity. So you can see that this thing, if you extend the line, it goes, I mean, it just keeps going away from, it doesn't converge anyway, it just keeps going endlessly. Okay, and that is exactly what the graph demonstrates, that it diverges. So just like I said, in the next set of videos, I'll be talking about convergence, tests for convergence. We are going to have like 4 or 5 tests of convergence like that in each video. One video, one test to drive the point home. So if you have not subscribed to this channel, you want to do that right now. And of course, hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know how helpful these videos are. Also, comment if you want me to teach a topic or solve a problem. I might be able to find time to do that. Then share share this video, share the link, do all that so that more people can have access to the great information going on here. So like it also to improve how far it goes. Till I come your way again, have a nice time. Bye.